Okay, so we're going to do what we said we were going to do in the last video. We're going to solve this by assuming that y is equal to a power series. And in particular, we're going to assume, just for simplicity's sake, that it's equal to a power series centered at 0. So something that has this form. Okay? I could center it at other values as well, but it's going to make the work more complicated. So to try to minimize the amount of work that we have to do, we're going to just assume this. If that's the case, I can find y prime by differentiating this term by term. Now think about this for a second. My index is going to change because, again, this is like a big polynomial, right? And if I plug 0 into this polynomial, my very first term is going to be a constant. When I differentiate that, my constant term goes to 0. It's going to disappear. So I'm going to lose what I would think of as the 0th term of this series, meaning the derivative will start at term 1, not term 0. Okay? Now, if I differentiate this just using the power rule, its derivative is going to look like n cn times x to the n minus 1. Remember, cn is a constant. And so this literally is just the derivative of that term. So now what do? Well, with these power series, I'm going to substitute each one of these into where they would go for this dE up here. So 4y prime plus y equals 0 is the same thing as 4 times this series, where we go from n equals 1 to infinity of n cn x to the n minus 1 power, plus y, which is that other series, n equals 0 to infinity, cn x to the nth power. Okay, and that's equal to 0. Now, before I can do any solving here, because the goal is to determine what those coefficients are. What do the CNs look like? Because if I can find the CNs, then I can take this general power series and give it a more explicit form. I can say exactly what it looks like, and that would be my solution. But to do that, I need to start by combining these two series into one somehow. So first of all, I can multiply that 4n. n equals 1 to infinity, 4n cn x to the n minus 1 plus n equals 0 to infinity, cn x to the n equals 0. Okay? But we have an issue here. So remember how we re-indexed and added those two series in our previous example. There was two things that needed to happen. The first thing that needed to happen was that the first term in each of these series needs to have an x to the same power. Now, does that happen? Well, if I plug a 1 in to this guy, specifically just looking at the exponent becomes 1 minus 1, or 0. So my very first term in this series is an x to the 0 term, a constant term. What about this? We're starting at n equals 0, so plugging 0 in here also gives me an x to the 0 term. So that first condition is met. Both of these series have the same type of term appearing first. But then the next issue is that we need the indices to start at the same place. And that's not happening. I have n equals 1 in one case, n equals 0 in this case. So like we did in the previous example, I am going to re-index this by making this n equals 0 to infinity. And remember, the way that we compensate and make this so that the series is actually the same one, just represented differently, is that we think if I subtracted 1 from this number to bring it down to 0, then anywhere I see an n in this formula, I am going to add a 1 to compensate. So this becomes 4n plus 1 instead of n. This becomes cn plus 1. And this becomes x to the n plus 1 minus 1, or just x to the n. We won't change anything about our second series, cn x to the n equals 0. Now I'm going to add these two, because I've now met both conditions that needed to be met. This adds into a single series, n equals 0 to infinity. And I notice that I have x to the n and x to the n. I'm just going to add their coefficients because those are like terms now. 4n plus 1 c to the n, cn plus 1, don't write the x, plus cn x to the n, okay? And that's equal to 0. So now we have a single power series. And this is what the coefficients on that power series look like. They look much more complicated than just CNs now. But we also have that this power series is identically equal to 0. And that's where we use that identity property. If this is true, then every single one of these coefficients for every single term in that series needs to equal 0. And so I can take that coefficient out, set it equal to 0, which gives me this. 4 times n plus 1 c to the n plus 1, or cn plus 1, plus cn equals 0. Or, equivalently, cn plus 1 is equal to negative cn over 4 times n plus 1. And this creates something that we call a recurrence relation. Okay? A recurrence relation, or a recursive formula for determining these terms, these coefficients rather, the CNs. So if I happen to know, for example, C0, if I know what C0 is equal to, I can plug it into this formula and it would give me C1. Then I could take C1, feed it back into this formula, and that will tell me what C2 looks like. Then I can take C2, feed it into this formula, and it'll tell me what C3 looks like. Okay, and that's the idea behind this. Now, this formula only tells us how to get each term in each coefficient in terms of the one that comes directly before it. And so if we trace this all the way back to the very first coefficient, C0 or C0, we don't know how to come up with C0. And so when n is equal to 0, then we are looking at the term C0, and we're just going to call it C0. Okay, and you'll see why that's okay to do once we get towards the end of this. When n is equal to 1, we are looking at the term C1. Okay? Oh, sorry. I meant to offset this. So I'm plugging n into this formula right here. We're not plugging anything in for n to get C0. C0 is just equal to C0. But then when I plug n equals 0, so notice that's the very first value of n that I would be using in my series up here, n equals 0. In this formula, that n equals 0 turns this into C1 because it's 0 plus 1 right here. And that would equal negative C0 over 4 times 0 plus 1. So that's just 4. Okay? Now, so what I've done is I've taken I've used my recurrence relation to find C1 in terms of C0 or C0. The next thing I would do is plug a 1 in to my formula here. So if I plug a 1 in, this becomes C2 right here. And that's equal to negative C1 over 4 times 1 plus 1. That's 4 times 2. But negative C1, I already found C1 in terms of C0. So if I substitute this in for the C1 right here, I have a negative, which makes this a positive C0. And then that 4, when I put that up here, is going to come down into this denominator and multiply to that 4, giving me 4 squared times 2. Okay? Let's do a couple more of these. If I plug in n equals 2, then I'm looking at C3 down here, which would be equal to negative C2 over, the formula says this would be 4 times 2 plus 1, which is times 3 there. That would be what this next term looks like. But C2 we've already found in terms of C0. So that would be equal to, okay, that's positive, which makes this negative C0 over, I have 4 squared times 2, and then that's going to get multiplied to 4 times 3, so that gives me 4 cubed times 3 times 2. Okay, and again, like we said in the one of the previous videos, we're not going to multiply these out explicitly because keeping this in this product notation is helpful. It reveals a pattern, okay? N equals 3. What happens with n equals 3? Well, that means we're looking at C4, which would be equal to negative C3, according to our recurrence relation, over 4 times 3 plus 1. That's times 4. But this is the same thing as negative negative, so positive C naught. And then again, this denominator is going to jump down here. I'm going to multiply 4 cubed to just one of those 4s to give me 4 to the 4th. And the other 4 is just going to stay put. 4 times 3 times 2. And there's a reason for that. It's because if I look at each one of these factors, it's looking like a factorial, right? If I did times 1 times 1 times 1, which wouldn't change anything, I'm getting factorials here. So I wanted to reserve that extra 4 right there to make sure the pattern continues. So we're seeing this pattern continue on and on and on, and every single coefficient is given in terms of that C naught, okay? So what does that mean then? Well, if I take my series, my original power series, y equals this sum from n equals 0 to infinity of c n x to the n, and then take those write it out term by term, using these cn's that I'm finding right here. My very first term should be c naught. Okay. Then my next term should be this coefficient, so minus c naught over 4 x. Remember, that would be my next term. It's an x term. Plus this coefficient, so plus c naught over 4 squared times 2x squared, minus that next coefficient. Let's see, y equals, where was it? Right here. C naught over 4 cubed times 3 times 2 plus c naught over 4 to the 4th times 4 times 3 times 2 minus, and you're seeing that pattern there, okay? So what I'm going to do is factor that c naught out of everything and then write this thing in summation notation. So y is going to be equal to c naught times the sum from n equals 0 to infinity. Now my first term here is my coefficient here is gonna look like a 1, and then this will be 1/4 x plus 1 over 4 squared times 2 x squared, and so on and so forth down the line. And we're also dealing with an alternating series. So trying to put this all together using some of the techniques that we talk about in Calculus 2, this is going to look like negative 1 to the power of n over, now notice my denominator, I have a power of 4 appearing in every denominator, where the exponent on that 4 matches the term that we're talking about. Here's the 0th term, first term, second term, third term, fourth term, and so on and so forth. So I'm going to have 4 to the power of n. And then we're also looking at factorials down here. So for example, even though I didn't write it, I could say that this is equal to 1 factorial right here. Notice this could have been put over 4 to the power of 0 times 0 factorial, which equals 1. So if I look at the factorials that are appearing here, that's 2 factorial. 3 times 2 is 3 factorial. This stuff multiplies to 4 factorial. The factorial is matching the exact term that I'm on. So that becomes n factorial down there. Okay? This is my solution. Now looking at this, if you're seeing the C naught and you're thinking, well, wait a minute, we never figured out what C naught is, you shouldn't be worried about that. And why is that? This was not an IVP. Remember, we were looking at a differential equation, in particular a first order equation. Remember that the general solution to a first order linear equation, a homogeneous one in particular in this case, is going to have a parameter. The C naught is that parameter. So we were expecting to find some arbitrary constant show up in here somewhere, and there it is. So that means that for any value that I plug in for C naught, I will get a specific solution to this DE, but this would represent the general solution in the form of a power series for that differential equation. Then, if this were an IVP, I could use my initial conditions to plug into the series here and try and solve for C naught. But we're not worried about that in this case. Okay, so that's going to wrap it up for 6.1.